Okay, welcome. So the topic of this video is ionization energy and electronegativity. These are two phenomena that you probably haven't dealt with very much in your previous science courses, so this may be a little bit new. So let's go right into ionization energy. You'll see it's really simple. All right, so basically, if you want to remove an electron from an atom, it's not easy. It takes energy. And let's look at a lithium atom as an example. So what I've done here is I've represented the nucleus with just a red sphere. You know that there's protons and electrons in there, but I'm just trying to show that they're, with the 3 protons in the nucleus of lithium, the total charge in the nucleus is 3+. And then I'm showing the first 2 electrons that are in the 1s orbital. Okay, so this is the n equals 1 principal energy level. And the 3rd electron, by the Aufbau principle, has to go in the n equals 2 energy level. And this would be a 2s electron. Okay, so now, who cares about removing electrons? Why is that a big deal? Well, when atoms interact with each other, say in a chemical reaction, or if 2 atoms are, going to form a chemical bond, many times the transfer of electrons is involved, and that requires energy to, move those electrons from one atom to another. So it's something that we've got to understand and got to be able to quantify. So, just for example, if we wanted to remove 1 electron from a lithium atom, probably the easiest electron to remove would be this outer one, okay? And this is what we call a valence electron. And so in order to do that, we're going to have to put some energy into this, okay? It's going to take a little bit of muscle, all right? So here comes the energy, and if we put just enough energy in there, then we can remove this electron, all right? And when we do that, as you can see, it goes away. It may have been captured by another atom, but what we're left with here on the lithium is now we only have 2 electrons, obviously. And because we've lost 1 unit of negative charge, the net charge is now positive, single positive. And we would call this a lithium cation. All right, now, we don't have to stop there. We can actually remove another electron. And so if we did that, that would take some energy, and then we would be down. We'd be down to 1 electron, and now the net charge would be lithium 2+. Okay, all right. So that's the process. You can do it multiple times, but let's back up. Let's back up to the original lithium atom. So when we remove the first electron, this is what we call the first ionization energy. Okay, so let me write that here for you. So that would be what we call the first ionization. And the energy that it takes to get that electron off, if you look that up in your book, you'll find is 520, and then the units might sound kind of weird at this point, kilojoules per mole. All right, but don't worry about the units. Just focus on the number for now. So it takes 520 units of energy to pluck off the first valence electron, and that is ionization energy, pure and simple. Okay, so if somebody said, "Hey, what's the ionization energy for lithium?" you would say 520, and if they want to know the units, kilojoules per mole. Okay, so that's what we call ionization energy. When you remove the second electron, that's simply called the second ionization energy, okay? And to do that, let's just kind of represent that. So if we're going to pluck off a second electron from lithium, then that's going to cost, more energy. And my question for you is, do you think that this second ionization is going to require more energy than the first one, or less energy, or is it just going to be the same? Well, one thing when you're considering, which one requires more energy is, if we go back to the 2s electron, notice how far the 2s electron is from the nucleus. it's, a fair amount further away from the nucleus than these inner electrons. And, remember, when you have opposite charges, they obviously attract, so there's an electrostatic attraction between the nucleus and the electrons. But the size of the force of that attraction, it goes down as the distance increases. All right. So conversely, the closer you get to the nucleus, the stronger that force is going to be. So I think hopefully you can kind of see the way this is going, because these 1s electrons are much closer to the nucleus. The force of the attraction to the nucleus is stronger, and therefore it's going to take more energy. And in fact, you may be surprised how much more. The energy to get that second electron off is 7,297. And again, that's kilojoules per mole. So it takes way more energy to get the second electron off than it did the first. Okay? All right, so let's summarize. So for lithium, the ionization energy is the energy required to remove an electron, and we can specify which electron we're removing. So the first electron we remove, that's the first ionization energy, and that costs 520 units of energy. To remove a second electron, that was the second ionization energy, and that took a lot more effort. So that was 7,297. Okay, so that's, in a nutshell, that's ionization energy. Now, let's take a look at the trends. Okay, so here's the periodic table. Since we're talking about lithium, let's start with that. If I grab my pen here. So the valence electron would be sitting right here. And so now we're just going to talk about first ionization energies when we talk about trends. Okay? When that valence electron is removed, that costs 520 kilojoules per mole. That's what we saw on the previous slides. However, when we go down the group, down the column, and go to sodium, sodium has a third shell, and so its valence electron is right here. And as you can see, it's further away from the nucleus. And so relative to lithium, sodium, it's a little easier to take its electron off. Okay, instead of 520, it's 496. And then if we go down the table even further, let's get to potassium. Potassium has 4 shells, and so its valence electron is even further from the nucleus, and as you might expect, it's even easier to get that one off, 419 kilojoules per mole. So here, over here, here's all the energies, so that you can kind of see there's a trend as you go down a group. It gets easier to pluck off that electron because it's, they're getting further from the nucleus. This is just to summarize. Again, I just want to be sure that you're solid with the definition. The energy required to remove an electron from an atom is called the ionization energy. Okay? The energy required to remove the first electron from an atom is called the first ionization energy. The energy required to remove an electron from an atom with a 1+ charge is called the second ionization energy. Okay, so this is a slightly different way of saying it, but it's exactly the same thing that I described earlier. Okay, now the trends overall. We're just going to be talking about first ionization energies when we talk about trends. And the trend is, let me just, I think I'm going to skip right now to this slide. Basically, as you go down a group, as you saw earlier, the ionization energies decrease. So it gets easier and easier and easier to remove that valence electron as you go down. Conversely, as you go from left to right, as you go across a period, it gets harder and harder to take that valence electron off. So the ionization energy increases going from left to right. Okay, now that's ionization energy. The second concept we got to talk about is electronegativity. Electronegativity is the ability of an atom, of an element, to attract electrons when the atom is in a compound. All right, what the heck does that mean? let me give you an example. Let's say we have a compound. Um, let's say we have hydrogen fluoride. Okay. If we draw this in a little more detail, the bond between the hydrogen and the fluorine is comprised of 2 electrons. So these 2 little dots represent electrons, all right? And so that's the bond between the hydrogen and the fluorine. But as we will see, the fluorine, it pulls on the electrons much more strongly than the hydrogens. And so what you're going to see is it's not shared. Those 2 electrons are not shared evenly between the hydrogen and the fluorine. The sharing looks more like this. All right, the electrons get kind of pulled over to the fluorine, and that's a consequence of the higher electronegativity of the fluorine than the hydrogen. In general, electronegativity values decrease from top to bottom in the periodic table, and they tend to increase as you go from left to right across a period. Let's take a look at some actual values. So these are electronegativity values, mostly for the representative elements. And you can see that, if you look for the highest value, fluorine. Fluorine is the king of electronegativity, 4.0. But then as you go toward the lower left part of the periodic table, the electronegativities are quite small. Okay. Here's like the general overview. So electronegativity, just like ionization energy, increases from left to right, and it decreases going from top to bottom. So that's one thing that's very handy. Ionization energies and electronegativities, the trends are the same. Now, let's do a little quick Spock check when we're done. If you had these 3 elements, how would you arrange them in order of increasing ionization energy? So, hopefully you've got your periodic table open, and I think you can see that all 3 of these elements are in the same row of the periodic table. They're all in period 3. You know that the ionization energy increases as we go to the right. Therefore, sulfur has the highest ionization energy. Aluminum would be in the middle. Sodium would have the lowest ionization energy. Finally, let's talk about electronegativities. For each of these pairs, if we're going to compare one element versus the other, which element has a higher electronegativity value? Okay, so for the first one, chlorine versus fluorine, they are both in group 7A, and if you fluorine is higher, it's above chlorine, and as you remember, electronegativity values go down as you go down the periodic table. So therefore, fluorine would have a higher. And don't forget, fluorine has the highest electronegativity value of any element in the periodic table. What about carbon versus nitrogen? Well, these 2 elements, as you can see, they're both in the second period, and we know that electronegativities get higher as we go to the right. Since nitrogen is to the right of carbon, nitrogen has a higher electronegativity value. What about magnesium versus neon? Okay, this is a bit of a trick question. From reading your textbook, you may remember that electronegativity values are not defined for noble gases, and neon is definitely a noble gas. So neon has no electronegativity value associated with it. So I guess by default, magnesium would have the higher electronegativity value. And then finally, we have arsenic versus calcium. And hopefully you can find arsenic. If you can find nitrogen, arsenic is 2 rows below nitrogen. It's in group 5A. And you'll see that both of these elements are in the same period. They're both in period 4. And because arsenic is way to the right of calcium, arsenic will have the higher electronegativity value. So again, I'll circle the ones with the highest electronegativity values: fluorine, nitrogen, arsenic, and then of course magnesium. Okay, thank you guys.